In this video, I'm going to look at another pH curve. I'm going to look at strong acid, weak base. Just before that, very quick reminder of the one that we did in the first video, strong acid, strong base. We're starting with a very, very low pH. So we've got a strong acid in the flask. We're adding base from the burette. Small, very small gradual increase in pH as the base goes in. As we're getting closer to neutralization, the pH starts to climb more rapidly. Then we get this magic one drop that sends the pH right through the pH scale, and we end up with a straight line, a flat line at the high pH end, showing that we've got a strong base. Another point to note is the pH at equivalence. So the equivalence point is the center of the vertical section. The pH at equivalence is 7 for strong, strong, and that's because the products of that reaction are neutral. And just a quick recap of what we mean by equivalence point. That is when you have equal moles or equivalent moles of acid and base present. So that's obviously when neutralization has occurred. So the first other combination I'll look at is this one, strong acid with weak base. So in brackets you can see my example. We've got HCl, aqueous HCl is going to be my strong acid, and my weak base is aqueous ammonia. It's always a good idea to write an equation for the reaction that's taking place, and you'll notice that instead of writing NH3 in the equation, I've written the formula of aqueous ammonia, which is actually ammonium hydroxide, NH4OH. So when you combine, when you put ammonia in water, you've actually got this chemical present, and it makes the equation a lot easier to write. So we've got the acid and the alkali making a salt and water. So if you had, I'll just show you what I mean there, if you had HCl and NH3, all you're going to be able to write is NH4Cl. So you can see I've written up there, I'm using 25 cm cubed of hydrochloric acid. That will be in a conical flask. Its concentration is 0.1 moles per decimeter cubed. And then we're going to add the ammonium hydroxide to that. So the starting pH is going to be very low because HCl is a strong acid. So we'd start sort of down in the 1 region, pH 1 region. And just as before, we would add small amounts of base, 1 centimeter cubed at a time, 2 at a time like I did on the previous video, and obviously the pH will rise very, very gradually. So the first part of this pH curve is going to look very similar to the previous one. And then when you get to close to the equivalence point, then the addition of this alkali is going to have a more marked effect, and the pH will start to rise. So you can see I've shown that there. But because this is a weak base, our final pH won't be anywhere near as high as it was with the strong alkali, the sodium hydroxide. So instead of finishing up at sort of pH 12, this curve's going to finish up still above 7, but much lower down than 12. So we'd end up with something that looks a bit like that. Now I just want to focus on the volume that would be here. So this vertical section, remember, is the equivalent, is when you've neutralized the acid. If we look at the mole ratio in this equation, this is a 1:1 mole ratio. So if our ammonium hydroxide or ammonia solution was the same concentration as the acid, we're going to need the same volume of alkali to have the equivalent number of moles. And so the vertical section, this would come down, and it would be, in this case, 25 centimeters cubed. I just want to pick up on something with regards to the pH at equivalence. So remember the equivalence point is sort of halfway here. So we've got an equivalence point around there. So if I say pH 7 is, let's say, here, you can see that the pH at equivalence is slightly below 7. Now, this hasn't been asked for quite a few years, and I'm just sort of second guessing the examiners may throw in a suggest sort of question. Why would the pH at equivalence for this type of reaction, why would the pH be below 7? So if you want to have a think about a possible reason for that, and then I'll go through the answer. So if we think about what we've got left in the flask at equivalence at this point here, if we've got equal numbers of acid and base, then we actually won't have any of that left, so we can cross them out. So all we've got in our flask is ammonium chloride, in this case, and water. So if we think about water for starters, water has a pH of 7, pure water does anyway, and so therefore it can't be that that's causing this slight drop in pH below 7. It has to be something to do with the ammonium chloride. Ammonium chloride is an ionic compound. It contains ammonium ions and chloride ions. Ionic compounds, when they're in water, they will dissociate into their ions. And so we would actually have ammonium ions and chloride ions present. So we'll focus on this one now, see if that's sort of giving you any clues. What can the ammonium ion do? Well, it can actually donate a proton. Oops, I forgot the plus there. So it actually can do this. And we've got this little equilibrium existing for the ammonium ion. What can we see? There's an H plus ion that's been donated by this salt, and therefore this must be slightly acidic, and that's why this pH is slightly below the 7.